Let me pin myself. All right, good afternoon, everybody. Welcome to a fun afternoon of organic chemistry, Chem 170, with your host, me, Dr. White. Hi, you two. Yeah, I guess number 3 is coming in now, too. Hello. All right, let's get going because we got a lot to do. We've got lecture and then our lab, and let's get going. All right, I've been talking about esters. And remember, how do you make an ester? You react a carboxylic acid. My software doesn't like putting in C's. And with an alcohol and acid, and you make an ester. And let's quickly practice this, and you'll understand why in a second. And why don't you start out with this one? What would be the organic product or products for the following reaction? And in case you haven't learned it yet, I'll help you out. You also get water, but that's inorganic. I tell you how biased organic chemists are against inorganic stuff. They are. I think everybody's just about done. All right, let's get going. If we look here, we have two substances. What functional group do we have here? A carboxylic acid. Look for what's different. Ooh, oxygen with a hydrogen and a carbon. That's an alcohol. And we're using acid catalyst. Remember, you can put it over the arrow or like I'm doing now. Organic chemists are lazy and we can do it either way. And you make an ester. Now, one of the beauties of organic chemistry and functional group of organic chemists, here we have a benzene ring, but I know of no reaction with an alcohol with a benzene ring with acid catalyst, so it won't. This is my R group. I have here my R prime, and that's, notice the carbon in the middle has the hydroxyl group, and the carbon with the hydroxyl group is the carbon the oxygen OR prime will be bonded to. So I have my benzene ring, carbonyl, carbon double bond oxygen, oxygen. What's my R group? Isopropyl. That's better looking 3. And that's the ester you make, isopropyl benzoate. And I showed you that if you take an ester, react it with acid and water, you get back the carboxylic acid and the alcohol you would have used to make that ester. And we'll learn later on this reaction is going on in your stomach. I'll go through the specific examples of what happens when you eat a fat or oil. All fats or oils, you'll learn later in the semester, are esters. And then I also taught you that if you take an ester, react it with water and a base, and the actual reaction I showed you was more general than this one. Where M is equal to lithium, potassium, or sodium. And you get back the carboxylate anion of the carboxylic acid you would have used to make that ester, plus the alcohol you would have used to make that ester. Yeah, and this is an important reaction because for many eons, this is how soap was made. I talked about the Grignard reaction, where you can make not one, but two carbon-carbon single bonds to new carbon, and you make two alcohols. When you react, there should be a two here. Two molecules of Grignard, second step acid and water. And generally, organic chemists keep the R primes very small so you can distill it off, and you're really trying to make this alcohol. But on my test, you should have both alcohols. All right. There's something I've been sheltering you from. That's a good word, sheltering. All the reactions I've shown you, except for the one with the benzene ring, have only one functional group in them. But in real life, you can have molecules with more than one functional group. Guess what? Unless there's special cases, which we won't be going into in this course, which I know, but we won't go into, each functional group, if there are two in a molecule, react like it's alone. So let's look at something interesting. Now, on the molecule, by the way, I'm going to turn the switch off. Will this be on the test? But at the same time, I'd ask you to pay a little attention because this is an important part of your daily life. Really? Yep. And here, this is a dicarboxylic acid, or we usually just say diacid. And you have a carboxylic acid here and a carboxylic acid here. And it has the common name, and I don't know if that's also the IUPAC name, terephthalic acid. And here we've talked about this alcohol, diol, dialcohol, ethylene glycol. I have one alcohol. Ooh, look, I have two alcohols. So let's look at what happens when you react these together. And this you do not have to copy down, but it's something interesting. Now, we just went through, which is why I repeated it again to refresh your memory. Fischer esterification, named after the great German organic chemist Emil Fischer. You take a carboxylic acid and alcohol acid catalyst, you'll get an ester. Well, if you take this and react it in acid, here's a carboxylic acid, here's an alcohol. And I've made this ester right here. Now the carboxylic acid at this end is still there, and the alcohol on this end is still there. And guess what? I can react this, say, with more ethylene glycol. And an acid catalyst. And here I have a carboxylic acid, here I have an alcohol, and I would get this new ester right here, and the rest still is there. Now, at this end, I have an alcohol. At this end, I have an alcohol. Guess what? I can react this with more terephthalic acid. Hold on, I'm having a bad ring drawing day. I've been lucky. I haven't had too many of those this semester. And here I have an alcohol, here I have a carboxylic acid, and I can react it in the presence of acid catalyst. Again, you don't have to copy this down. Or I'll do this then is an alcohol. And I now have this molecule. And notice at this end, I have an alcohol that can react with more terephthalic acid. And at this end, I have a carboxylic acid that can react with more ethylene glycol. And this can keep on going and going and going, like the Energizer Bunny. Bang, bang, bang. But anyways, there's a repeating unit. If you were to look at this, that a certain part of this repeats over and over again. If you were to do this, say, about 1,000,000 times, yes, 1,000,000. And what's that repeating unit look like? This. Here I have my ester, and at one end I had a carboxylic acid, the other I could have an alcohol. And here N means this is repeating over and over again, just like boxcars in a long freight train that are all the same. Now, how big can N be? It can be up to 1,000,000 or more. 10 to the 6 is 1,000,000. So this can be very large. Now, what would be the name of this compound? Good question. Well, it's an ester, so it has that ATE ending. It comes from terephthalic acid. I don't want to give it away yet. No. Anyways, so because there are many of them, we use the word poly. It comes from ethylene glycol, so it's called polyethylene, and terephthalic acid, drop the IC in the word acid and add ATE. So this is called polyethylene terephthalate. Polyethylene terephthalate. Polyethylene terephthalate. Hold on one second. And polyethylene terephthalate, oh, that hurts my jaw. That's a lot to say, polyethylene terephthalate. I'm thirsty. Well, that's good. Polyethylene terephthalate. I'm still thirsty. And why should you learn about that? Well, being a lazy organic chemist, instead of saying polyethylene terephthalate, I'll say PET, which is what this bottle is made of. The polymer I just showed you, plastic bottles for beverages, water, and other things are made of a polyester that you react terephthalic acid and ethylene glycol. So if you're wondering, why am I learning this stuff about how to make an ester? Well, we used to make plastic bottles. And now I can undo that. And this is the structure of plastic 2-liter bottles or other bottles and other plastics. And there are other polyesters we use in our daily life also. My glass lenses are a polyester. They're called polycarbonate, but they're really a polyester. Yeah, guess what? We finished this chapter. Yay, we've finished it. And if you look at the schedule, which I did this morning, we're right on track. We're doing good. So, a couple things. First of all, let's do it Monday. I will go through the carboxylic acids and esters, or carboxylic acids and their derivatives problem set this Monday. Make sure you try it before I do. And the other thing that means is it's new chapter time. And I better warn you about this new chapter, because this new chapter has stuff that's near and dear to my heart. And I mean near and dear, like it paid my salary, helped me buy this house, helped me buy a couple of cars, got me around the world to various places. And I also have about 9 US patents in this area that we're going to talk about. So remember I talked about ketones and aldehydes are my comfort functional groups when I don't feel good. You know how you know about comfort food? When you're not feeling good, you just eat something that makes you feel better. My dangerous ones are Lay's sour cream and onion potato chips. Those are good. French fries are good too, but I like the Lay's better. But anyways, this chapter contains my other very, very good comfort functional group. What's all this about? Well, let's go into it. Plus, I got some really neat stories to talk to you about. And that new chapter, actually 2 chapters from the book I combined, is our amines, amides, and heterocyclic compounds. And Dr. White, me, or I am a world authority in amines, amides, and a derivative of amines. I don't work that much in heterocyclic compounds, but I know. Now, what is an amine? Amine is an organic derivative, something made from ammonia, which one or more of the hydrogen atoms on nitrogen are replaced with an R group. That can be alkyl, cycloalkyl, or benzene ring aromatic, and we call that aryl. So what are we talking about in amines? In case you forgot, ammonia is this structure or compound. And let's look at something I haven't done this whole semester. If we look at the Lewis structure of ammonia, each pair of dots represents a single bond. And notice right up here, unlike carbon, we have non-bonding electrons. And for the most part, they're usually not involved in a chemical bond. So if you notice, how many bonds to nitrogen are there? I got to be careful. I always say carbon. 1, 2, 3. And therefore, for amines, nitrogen has 3 bonds, and for a amine derivative, the non-bonding electrons can also be bonding, and you could also have 4 bonds to nitrogen. So for amines and a special derivative, I should say derivatives. So this is a little tricky, and students get, I don't know, confused, but it's true. Carbon, you know this. Oops, still broken. But for nitrogen, you can have 3, or you could have 4 bonds to nitrogen. And so you can have either one because nitrogen has non-bonding electrons. So as I have on this slide here, nitrogen has 5 valence electrons, and it can form 3 covalent bonds to complete its octet. And it has a lone non-bonding lone pair, is sometimes called, also known as non-bonding. This will never be on a test, but nitrogen has 5 valence electrons, and that would be the Lewis structure, and it wants to have 8, so it can share with, let's say, carbon, R groups. So those are amines. Now, there are different types of amines, and I'm going to turn the switch off for this slide, but I will use this terminology, so you should know what I'm talking about. Now, here's ammonia. If I replace one hydrogen with an R group, I have a primary amine. Dr. White loves primary amines. They've been good to me. I've been good to them. Now, if you replace 2 hydrogens from ammonia, and the R groups can be same or different, we have what's called a secondary amine. And again, I'll never ask on a test, but I will use terminology in this chapter. Now, for a tertiary amine, I replaced all the hydrogens. Now, there's something called a quaternary ammonium salt, and I should warn you, I'm a world authority in quaternary ammonium salts. And the other thing, well, let me show you what it is. I didn't show it, but I'll do it now. There's also these non-bonding electrons, or lone pair electrons. Now, it turns out in nitrogen, you can use those non-bonding electrons to form a bond. And if you form 4 bonds to carbon, 4 bonds to nitrogen. Nitrogen in one of these is providing both electrons. And because of that, it has a positive charge. All molecules have a net zero charge. So if this is positive, called a cation, you need an anion. And for this class, I'm going to stick to the halogens. This is an anion. And therefore, in quaternary ammonium salts, you have 4 covalent bonds to nitrogen, plus an ionic bond between the nitrogen and the halogen, anion. And I'll teach you later, but X here can be, it can be fluorine, but that's rare, so I won't teach you that. And you're familiar with the halogens, chlorine, bromine, and iodine. And these are quaternary ammonium salts. And again, I'll never ask you what kind, well, you should know this is a quaternary ammonium salt, but I won't ask on a test, is this a primary, secondary, or tertiary amine? But you should all know that 3 of these structures are all amines. Each one of these is an amine, and that you should know. Now, I better warn you, and I'm going to try and be a good chemist. If you work in quaternary ammonium salts like I have for decades, if you're working in industry like I have, you don't call them quaternary ammonium salts, you call them quats. That's short, and organic chemists are really lazy. We don't like to say big words if we don't have to, but I'm going to try and be a good teacher and not use slang quats when I talk about quaternary ammonium salts. Now, nomenclature for amines, nobody uses IUPAC unless you put it in a patent or in a legal document. Even then, you use common names. So I'm going to only ask you to learn the common names. And what I have here is incomplete. Let's do an amine. And something tells me I haven't done this. All right, everybody see my whiteboard now? And that's not the slide I want. All right, do you see common names on your screen right now? Give me a thumbs up if you can. Thank you. All right. Now, let's look at this molecule. Look for what's different. What's not carbon, what's not hydrogen. Ooh, a nitrogen. And notice it has carbons here and 2 hydrogens. This is an amine. It's a primary amine. And how do you do the common name? You name each alkyl group on the nitrogen as an alkyl group. In this case, N-butyl. And then add the word amine. Sorry about this instant editing. And by the way, you can always come back and look at this video if you don't want to write this down right now, because I've been keeping up to date with our videos. And I guess you people have been watching them too, which is why I do this. All right, so this would be butylamine. Now let's look at the following. Remember, there's 3 bonds to nitrogen unless you're talking about a quaternary ammonium salt or a quaternary ammonium amine. And here we have 3 bonds. Now, a couple things I need to teach you. This is one way of drawing this secondary amine. Now, notice there are 2 methyl groups. See, 6 months ago, would you know what I was talking about if I said methyl group? Doesn't it feel good, all this stuff you're learning? I hope it does. Now, the normal way, since organic chemists are lazy to write this, would be using the brackets. And both of these are the same identical molecule. I don't know if you know in math, 3 lines means identical. And more of the times, being a lazy organic chemist, I'm going to write it this way, not this way. But on a test, you can write it either way, because I have a piece of paper from Michigan State University telling you I know this, my PhD degree. Now, what would be the name of this? Well, how many methyls do we have? 2. So this would be dimethyl amine. And since I haven't shared any fun with you yet today, I'm going to let you give the common name for this structure. And give me a thumbs up when you're done. All right, I think everybody's done. So let me get the word. Look for what's different. Ooh, a nitrogen. It's got R group here, and a hydrogen. Remember, in amines, there's 3 bonds to nitrogen. This is an amine. And therefore, we have, and because it's common, there's no rules which goes first or second. You could write ethyl. That's what this is. And then here we have, oh, it's our old friend, the methyl. Amine. And that's how you do it. Now, you could have also written methyl ethylamine, and that's perfectly correct too, because this is a common name. Now, one of the things, since I'm asking you to be able to write the common name of amines and also later on other derivatives of amines, not the IUPAC, on test number 3 for nomenclature question, if I give you a structure, I will say, give the IUPAC or the common name for the following molecule, 3 points each. And why don't you try this one? What would be the common name of that molecule? And Tam, we're talking about a new chapter, new functional group called an amine. And what you missed will be in the videotape, so you'll be able to catch up. Speaking about ketchup, anybody pick up a bottle of ketchup and see that it contains vinegar, which is acetic acid and water? which means it's got a carboxylic acid in there. Did anybody pick up a bottle of vinegar and say, oh, this contains acetic acid? I'm going to stop for a second, go full screen. Did you pick up a bottle of vinegar and say this contains acetic acid? It's a carboxylic acid? Or did you happen to pick up a bottle of nail polish remover? See, I took my nail polish off already. I don't polish my nails, even though my grandfather and brother-in-law, even he used to for many years in barbershops, they used to put clear coat nail polish on men's nails. I don't think that's done anymore, but anyways, did you look at a bottle of nail polish remover and see it has ethyl acetate, which is the common name for an ester? Did you do that? Remember, when you leave my lecture, you can still think about organic chemistry. It's all around us, it's everywhere. All right, let's take a look at this one. And the question is, what's the common name for this? Well, if we look at this, oh, I've got 3. And what is this in ethyl? How do we say 3 in organic chemistry? Tri-ethyl amine. Now, if you notice on this one, how come there are no hydrogens? Well, there are 3 bonds to nitrogen, and they already have 3. So that's why there are no hydrogens there. And let's go the other way. Why don't you draw the structure for ethyl isopropyl amine? For those who came in late, don't forget, Monday, I will be going through the carboxylic acid and their derivatives, really esters, problem set. So I highly recommend you do it before I do. Thank you, Joe. Thank you, Calvin. Calvin, is the weather still bad in Champaign?
No, it's been a little nicer the last day or two.
Good. You
A
don't
little chilly later.
I was going to use a term you might not know of. Have you ever heard the term galoshes?
Yes.
All right. I don't know if I was just going to pull a generation gap, but with all the rain you said you were having, you have your rubber boots on.
I wish I had some days.
Really? I have some waterproof boots that I wear when I do my snow blowing. But I've had rubber boots since I was, in grade school? Remember how your parents bought them for you?
Mm-hmm.
All right, let's get going. All right, how do you write this? Draw the structure. You start from the right, move left. Oh, an amine, I know what that is. And on there's an isopropyl and an ethyl. So amine, nitrogen, one side, it doesn't matter which side you put the ethyl, and the other isopropyl. Now, how many bonds should nitrogen have? And since you only have 2 here, 3 minus 2 equal 1, that tells you there's a hydrogen there. Similar to carbon, but here we're talking 3, not 4. And that's how you do it. Oh, let's do another one. And why don't you draw the structure for diisopropylamine? Thank you, Megan. You're really in the shadows today, Megan. I'm just kidding. Anybody ever hear the radio program, The Shadow? Why? Where have you people? Look on Google. Notice I'm old school. I don't use Google as a verb. All right, everybody done? All right, let's do it. How do you decode this? You start from the right, move left. Amine, nitrogen compound. Isopropyl, I know what that is, and di means 2. So this has 2 isopropyl. Now there are 2 ways I could draw this. And there are 3 bonds to nitrogen. That would be one way. And this would be another way. And they're both the same. By the way, everybody say hello to my old friend, diisopropylamine. When I was in graduate school, I used a lot of this compound where I made a special base to make enolate anions, which you know what they are, enolate anions. And this was part of my PhD thesis research, and I used this molecule a lot. I mean, a lot. Now, just to show you why we use carbon and not IUPAC, here you have, and the switch is totally off for this page. How do you name an amine by IUPAC rules? Well, you name the suffix, that part at the end, amine, instead of like an alcohol, OL. Find the longest chain with the nitrogen and name it as an alkane and drop the E and add amine. Now, secondary and tertiary, and this is different because you don't see this with carbon functional groups. The secondary and tertiary amines the prefix capital M, that's why I'm careful when I draw small n and capital N, is used for substituents on the nitrogen. Now, let me give you a quick demo. This will never be on test. And what would be the IUPAC name for this? Longest chain 4, butane. You drop the E, add the word amine. What carbon is the nitrogen on? Carbon 1. Now look at right here. We have that methyl group is on the nitrogen. Again, you don't have to write this down because I'll never ask this on a test, but that's a methyl group. If I could spell it right. actually not spelling. I've been pretty good this semester. Didn't give myself enough room. And it's not on the chain, it's on the nitrogen. And we do this, capital M, says N-methyl-1-butanamine. But the common name is N-butylmethylamine, which is a lot easier, at least in my mind, to generate just as opposed to the IUPAC. And that's how you do amines. Now, one thing I should point out, when amines are in this switches off, but I thought I'd tell you, when amines are in amines where additional functional groups are present, the amine group is treated as a substituent, and it's called an amino group. And where does that play a role? In this type of molecule. And notice we have an amine and a carboxylic acid. If I could spell it right. It must be Wednesday because I'm having spelling issues. I tell you, I was always the first one down in spelling bee. So you could call this, since it's this would be the substituent, it's called now an amino group in this molecule. And you could call this whole thing here an amino carboxylic acid. An amino carboxylic acid. Did I tell you organic chemists are lazy? I'm not going to call that an amino carboxylic acid. I'm going to call that an amino acid. And later in the semester, I'll be teaching you about amino acids. And amino acids are a molecule that have an amine group plus a carboxylic acid. And they're called amino acids. And they're quite important for life on this planet, like you and me. And if I look at the clock, oh no, I went a whole minute over. Let's take a break and come back at 1:56 and we'll do today's lab. 5-minute break. I'll see you in 5. I'm back. Profound, huh? All right, let me open up two things before we get started with our lab. All right, one thing I just realized, bad, Dr. White. I forgot to attach something that should be attached, and later today I will, for you to download besides the lab for today's lab. I'll take care of that. All right, today's lab deals with aldehydes and ketones. Again, one of my favorite functional groups. So let's look at today's lab. And today's lab deals with aldehydes and ketones. And remember, as you all learned and did very good on test number 2, this is an aldehyde. Don't forget, today's lab is due today from last week. And this is a ketone. Now, today's lab, like all the labs I wrote for this class, which I did, we'll go through some basic fundamentals dealing with aldehydes and ketones. The important thing is an aldehyde or are aldehydes and ketones soluble in water? And what you'll do is you'll take some clean small test tubes if we're face to face, fill them up about halfway with DI water. DI stands for deionized. You take the ions out of the water, so it's this almost not pure water, but pretty close to it, deionized water. And we use that in the lab. And in each test tube with the water, you put about 5 to 10 drops of the following aldehyde or ketones, and you mix it. Now, when you're mixing a test tube, small test tube, remember, never, ever shake a test tube like that, because you can get chemicals on yourself or your neighbors, or worse, the instructor. One way of doing it is, if this were a test tube, hold it very firmly and whack it 3 or 4 times, and it'll mix it. Don't tickle it, that won't mix it. You really got to hit it hard. Now, the other thing which we do have at the labs at ECC are called vibro mixers, and they're based with a motor in it, and it's got a disc rubber, and you can set it so when you push down this disc, it starts vibrating real fast. And that also mixes it. And students love those, so do I. And we use either one. And you only have to do that, push down on it for about 5-6 seconds, and it's mixed quite well. And then you'll observe, is the material in the test tube, the liquid, homogeneous, the same throughout? Then it's soluble. If there are 2 layers, it's insoluble. Now, notice right here, I'm asking you, underneath the name, draw the structures for the compounds in the table below. So right here, you should draw the structures. And if you notice, I give you the data. Now, students, when they do this and say, Dr. White, most of those were insoluble. I said, hey, you got the right data. So deal with it. I don't say that to them, but I'd like to. All right. Now, since we're not going to smell anything, let's just omit this part too. But benzaldehyde, you've already smelled, and smells like cherries or almonds, vanilla or vanillin, vanilla extract, that. And the rest of these, most students say they smell a little like gasoline, but this we're just omitting. I would have put in. Now, let's talk about the oxidation of aldehydes and ketones with potassium permanganate, KMNO4. And to make this go faster, this is usually acidic potassium permanganate. You put a little acid in there. And let's go through this reaction, which I really didn't. That's not what I want. This is what I want. I talked about this as an oxidation, but let's look at this. If you take an aldehyde and oxidize it with potassium permanganate, this is purple solution. It's in water. And these are usually clear or slight yellow, very slight yellow. Well, if you oxidize it, so you learned this for a chapter on carboxylic acid, so I didn't put this in test number 2, you get a carboxylic acid. This is oxidized. Well, this is reduced to manganese dioxide. And you've seen this before. And what happens is, this is what I call a muddy brown color. So if you have an aldehyde and you oxidize it with potassium permanganate, you'll see inside that test tube muddy brown. Now, if you have a ketone, well, in this case, guess what? If you oxidize it with potassium permanganate, you get no reaction, which means the solution will stay purple because the potassium permanganate doesn't react, isn't reduced to manganese dioxide. So this is a very good way in the old days before they had electronic equipment like IR, it's called infrared spectroscopy, nuclear magnetic resonance spectroscopy, NMR, or carbon-13 spectroscopy, C13 NMR, which Dr. White knows these things, but in the old days, long ago, you have an aldehyde or ketone, well, you'd react it with potassium permanganate and see does it go muddy brown or stay purple. And that will tell you whether it's an aldehyde, muddy brown, ketone stays the same purple. So in this section of the lab, and by the way, here's a nice YouTube if you'd like to watch and see that muddy brown color, feel free to look at that. And in the dry test tubes, you put about 1 to 2 milliliters of the potassium permanganate reagent. And to help students out, That's about 2/3 of an eyedropper we use at ECC. And then add about 5 drops. That means the tilde, about 5 drops of the compound being tested, and mix it the way I showed you. Never go like this, either hit it or use the vibro mixers. And notice here, I have benzaldehyde, cyclopentanone, and then to make it interesting, I have cleverly labeled unknown 1. And there's the results. And you'll see in the question area, there are questions about, or a question about unknown 1. Now, I feel real sad now because the next part is really fun for students to do. And this is called a cross-aldol condensation. And this is a reaction which you react an aldehyde with a ketone. In this case, notice 2 aldehydes, benzaldehyde with acetone. And here, I should also have here, the solvent is ethanol, not water. And you make this very complex molecule, which has the common name dibenzyl acetone. And let's take a look at this, because this one I'll show you to YouTube. Sorry about the commercial. Let me skip it. Let me do this. I'll restart this.
So this reaction is the reaction between aldehyde, where we're using benzaldehyde, and ketone. So the ketone we're going to be using is just acetone. So these R groups are just examples. But it can be used with any ketone. We're going to run it. The solvent's going to be methanol, and then we're going to have some alcohol condensation is basic catalyzed. So we're adding molecular sodium hydroxide. And sometimes it reflect or scatter the UV light. Because of this, this compound is used in sunscreen label, so that you can read and how much we have here. Exactly 1 ml.
I'm going to fast
So 1
forward.
ml aldehyde. We have
They're mixing everything together. This is called a magnetic stir. We do this by hand.
start coming yellow color.
And it takes about 5 minutes. And if you notice, let me back up a little.
Wait for some time.
Notice how it went solid in there? That solid is the benzaldehyde reacting with the acetone to make dibenzyl acetone. Now, I don't know why this person's adding more. You don't have to. And if you let it react longer, you'll see the solid form in there. And there's the solid. Now, what they're going to do is cool it down. We don't use, I just have people put it right in an ice bath. If you're careful, you don't have to clamp it. And that helps precipitate out the solid. And to remove the solid, this is called the Buchner funnel. The Buchner funnel, this white part, has a piece of filter paper in there. Underneath the filter paper are holes. And he's wetting the filter paper. Underneath, this is called the Erlenmeyer with a sidearm. And it's hooked up to, see this big rubber tubing? It's a reddish color. That's hooked up to a vacuum line. That's just like your vacuum sucks dirt off the floor. This pulls air and liquid through the Buchner funnel. And now he's wetting it with water. If you look at the bottom, you'll see there was liquid down there, or ethanol. That's the solvent he used. And now he's going to pour, watch this. These are really cool to play with. And you can see at the bottom, there's liquid in the Erlenmeyer, the glass. And you should never shake. You should use a spatula. See how the liquid is coming in the bottom here? And he's getting the last bit out of the Erlenmeyer. For our lab, we don't have to do this. And see how it also will wash some of the solid off. And let's fast forward a little. And after letting it sit with the vacuum, the yellow solid, that's the dibenzyl acetone right there. Come on, focus, please. And this part is this waste. And you let it air dry for 5 to 7 minutes. And you have a solid there that you can do a melting point on. And let's see. And see how he's taking the filter paper out with the solid product on there. And that's your dibenzyl acetone. He didn't dry it long enough, I don't think. But anyways, in this reaction, I have where you mix the different things together. You have the benzaldehyde, and that flask he had is called the Erlenmeyer flask, and that's designed to mix things well by your hand, or they had a magnetic stirrer. We don't use that at ECC, you do it by hand. And you do the different steps, and you follow, this is like falling off a log. You can't mess up unless you don't have the things correctly measured. And I've rarely ever had a student mess up, like almost never. And you then swirl it and then put it in the ice bath and use the Buchner funnel like I showed you and dry it. Now, we don't have enough time to do the melting point. Oh, we do, that's right, for this one. But if you were in there, you'd get this melting point. And that's how you do it. Now, there's something I want to show you. Dr. White's going to have some fun. I will post this in the lab later today. And this is called the mechanism. What happens step by step. And also I'll explain why this is called a cross-aldol condensation. Here I have my 2 molecules of benzaldehyde, my acetone, sodium hydroxide and ethanol. And what's the important thing? First step, you form the enolate anion of acetone. And you learned about this. By the way, this will never be on a test, but you should pay attention. And this sheet I will be posting on the lab in D2L. In real life, I'd hand this out in the whole class. Each one get your own sheet. So you have in acetone, not 1, but 2 alpha carbons, and each one has hydrogens. Now, if you look at the benzene ring here, this carbon attached to the carbonyl carbon has 4 bonds to it. I don't show it here, but let me rewrite it. This is the alpha carbon in benzaldehyde. It has 1, 2, 3, 4 bonds to it. So there's no hydrogen on that carbon, which means you can't form the enolate anion with benzaldehyde, which makes it very unique to do things with, which we're doing in this lab. So you form the enolate anion, and then this attacks the carbonyl right here, the benzaldehyde, to form this molecule right here. Now, one thing I haven't taught you in lecture, but I'll teach you now, is whenever you can have conjugation, alternating double, single, double, single, double, single bonds in a molecule, that makes it very stable. And if you notice this molecule right here, I have a hydrogen here, hydroxyl group, 2 hydrogens, oxygen, H2O, water. And whenever you can form a stable leaving group to form something more stable, the water says, hey, I'm out of here. And that's what minus H2O means. And between these 2 carbons, you'll form a double bond. And now you have, like right here, double bond, single, double, single, double to the carbonyl. This is very stable, more stable than the molecule. And this happens immediately. Now, if we look at this new molecule right here, we have on this carbon of the molecule hydrogens, and this is the alpha carbon, and we still have base present, so this can form this enolate anion right here. And that enolate anion will react with the second molecule, benzaldehyde. Let me get me out of the way here, to form this molecule here. And once again, if I lose OH here and one of these H's, 2 hydrogens, 1 oxygen, H2O, water, I'll form a double bond and I'll form more conjugation. And this loses water immediately. And that's the steps how you make this compound. Just think about that. All that's going on when you react those reactants or starting materials together. And the whole key of this is the base forms the enolate anion, because that's what does all the neat stuff. And down here, this part 2, omit, what did you learn about the relationship of aldehydes, ketones, and their odor? That you don't have to answer. And don't forget to answer the rest of these. And don't forget, on the first table right here, I don't even call it table 1, I should, draw the structures underneath the names of these. And with that, I'm done. If we had been in the lab, I'd say, all right, it's time for you to go into the lab, but we're not in the lab. I think it's safer with the pandemic still raging out there. So don't forget, if you have any questions, come to my office hour tonight, or it's actually an hour and 15 minutes. One thing I should mention, if nobody's there while I'm waiting for people to show up, so I'm required to be there, I'll go on the internet and look at things like trains. I'm a train enthusiast. My father got me hooked on that when I was about 4.5, 5. He got me a Lionel train set. And also he used to take me down to the train yards on the weekend to watch these monster engines come in and being serviced. We'd be on the fence right outside the train yard. Oh, what a beautiful time of my life. But anyways, if you see me looking at other stuff, just say something and you'll get my attention. But if you have any questions, stop by. If not, I'll see you on Monday. Don't forget, on Monday, I'm going to go through the carboxylic acid and ester problem set. With that, gang gesund, be healthy. Bye.